Hey, the next topic we're going to talk about is linear expansion. That's the next little topic in our thermodynamics unit. That's still chapter 13. It's pages 357 to 360 if you're following along at home. Linear expansion, sometimes also called thermal expansion. When most things are heated or cooled, they either expand or contract. With most things, if they're heated, they get larger. If they're cooled, they get smaller. Different things expand and contract different amounts. It's completely based on the temperature change as well as what material things are made up of. Maybe you've seen some of these things before. The first one on the left, these are expansion joints in a bridge, right there. The reason why those are there is because when the temperature changes, especially in a climates like this where there's a huge range in temperatures from winter to summer, the bridge itself expands and contracts. These expansion joints are here so the expanding and contracting of the bridge doesn't crack the pavement, but rather these things just move back and forth. It kind of provides some leeway for the bridge to expand and contract. This is buckling of railways, where the railroad tracks expand and bend, and it's caused hundreds and hundreds of train derailments, even now, not just back in the wild, wild west, but today that happens. This is a crack in a glass, where it was probably heated up or cooled too quickly, caused the glass to expand or contract, which then caused it to crack. That probably explains why my windshield cracked the other day and I had to have that replaced. It also explains why we use special glassware when you're doing any chemistry labs or any labs where you're like heating anything up or baking anything. You don't just use regular glass for that, you use special Pyrex because of the properties of that glass. What just happened? I just clicked on something. Hold on, let's run that back. There we go. Thermal expansion. So yeah, like I said, when most things are heated and cooled, they expand or contract. This relationship is linear, and it depends completely on the material. The equation for this is the change in length of the material is equal to alpha. That is not fish. That alpha is called the coefficient of linear expansion. This L naught or L0, that's the original length. I can't see where the mouse went. This is the original length of the thing, as well as the change in temperature. Just to kind of make this a little bit clearer, change in L, that's the change in length, that's measured in meters. That alpha, that's the coefficient of linear expansion. The unit for that is 1 over degrees Celsius. There should be a degrees sign there. And that's completely dependent on the properties of the materials. This right here, there's a value for like steel, there's a value for like marble. Every different material has a different coefficient of linear expansion, meaning that different materials expand or contract different amounts. LO is the original length, also measured in meters, and change in T or delta T, that's the change in temperature measured in Celsius. We don't like to use Fahrenheit. For this, we can use Celsius or Kelvin when you're using this equation. Take a minute, make sure you got this copied down, hit pause, go on to the next slide. On page 358, you'll see that there's a table of coefficients of expansion that I could not somehow copy and paste onto this PowerPoint. My bad. Just imagine that it's there, or better yet, look at your book. You see that different materials expand and contract different amounts. Coefficient of linear expansion, that's alpha, or that fish-looking thing. The unit for that is 1 over degrees Celsius. And you guys can see that if you look at where it says ordinary glass, which is like the 7th or 8th one down, that has a higher coefficient of expansion than Pyrex glass does, which is why when we do labs and when you cook, you want to use Pyrex glass rather than ordinary glass, because ordinary glass expands and contracts more than Pyrex glass does when it's heated and cooled, so there's a higher chance that it will crack. You just take a couple seconds, take a look through this coefficient of linear expansion chart, which again, sorry, I couldn't put it up on the screen. Hopefully you got your book. There's also a coefficient of volume expansion, which we're not going to talk about, but it's just 3 times the coefficient of linear expansion. because instead of expanding in one direction, it expands in three directions. We're not going to talk about that, but that's there also if you want to take a look. To do a sample problem, the steel bed of a suspension bridge is 200 meters long at 20, again, my fault for not having units, 20 degrees Celsius. The range of temperatures is negative 30 degrees Celsius to 40 degrees Celsius over the course of the year. How much will that bridge expand and contract? So grab a piece of paper, open your book to page 358 so you can take a look at that table of coefficient of expansion. Hit pause, give that a shot, and then I'll run through the calculation on the next page. So hit pause. Okay. How I'm going to do this, there we go. Oh, this one does have units. That's cool. The first one, this left-hand column is going to be for the contracting. That's going to be when it goes from 20 degrees Celsius to negative 30 degrees Celsius. When things get cooler, when the temperature goes down, things shrink, they contract. So I'm going to start with my equation. The change in length equals alpha, coefficient of linear expansion, times how long the thing was in the first place, times a change in temperature. I am going to look up this value for alpha from the table on page 358. If this was an AP exam and they wanted you to do a calculation with this, that you would have to be given this. You don't need to memorize any of these coefficients of linear expansion. I got this from the chart on page 358. Coefficient of linear expansion there is 12 times 10 to the negative 6. The units I put in these funky bracket things just to make it easier to type. But the units for this is 1 over degrees Celsius times the length of the bridge, 200 meters, times negative 50 degrees Celsius, because when it's contracting, it goes from 20 to negative 30. So 20 minus a minus 30 is, negative 30 minus 20 is a change of negative 50. My fault for misspeaking there. Celsius on the bottom, degrees Celsius on the bottom for the units. Pointer option. Ooh, I can do that. Cancels. So I'm left with a change in length of negative 12 times 10 to the negative 2 meters. What this means is that bridge gets 12 centimeters smaller over the course of the year. For the expanding, same equation, same process, there's just a different change in temperature. Now the change in temperature is not negative because when it's expanding, it's going from 20 degrees Celsius to 40 degrees Celsius. So the change in temperature there is 20 degrees Celsius. I can also cancel my degrees Celsius on the bottom in my alpha with degrees Celsius on the top over there. And we are left with a unit of meters. And the amount that the bridge expands is 4.8 times 10 to the negative 2 meters. So that gets 4.8 centimeters larger over the course of the year when the temperature goes from 20 degrees to 40 degrees Celsius. So that's why that they put those. That's why they put these expansion joints in bridges, because it will shrink roughly 12 centimeters and grow roughly 5 centimeters over the course of the year. So you have to have these expansion joints in there or else your bridge will crumble, and that will be bad news for the people that built the bridge. That's pretty much it for sample problems and presentation of this equation and where it comes from. Due next class at the end of chapter 13, which is page 380, 3 questions, question 7 and question 9. Question 7 deals with thermal expansion, which is this stuff. Question 9 deals with thermal expansion, which is this stuff. And then question 26, that deals with the temperature conversion that we talked about, or I talked at you about in the last video. So that's due next class, 3 questions. If you can't get it perfectly fine, that's okay, just from watching the video. Be neat, show your work, include units, draw a picture, everything that we do when we're in class. I'll check it when we're there. Okay, have a wonderful day.